Hello, welcome students. I am Rekha Thorat, Associate Professor. Today, I am going to discuss with you CAYLEY-Hamilton theorem. Statement of this CAYLEY-Hamilton theorem is every square matrix satisfies its characteristic equation. That is, if determinant of A minus xi equal to A naught plus a1x plus a2x square plus up to last term is plus an x raised to n equal to 0 is the characteristic equation of a square matrix A, then a naught into I plus a1 into A plus a2 a square plus up to last term is plus an a raised to n equal to 0. That means if A is any square matrix, then you know that its characteristic equation is determinant of A minus xi equal to 0. And if determinant of A minus xi equal to A naught plus a1x plus a2x square plus up to an x raised to n equal to 0, then we have to prove that square matrix A satisfies this characteristic equation. That means replacing x by matrix A, this equation is satisfied. That is, we have to prove that a naught into I plus a1a plus a2a square plus up to an a raised to n equal to 0. Let us prove this theorem. Let A equal to square matrix Aij be a square matrix of order n. Then A minus xi equal to square matrix. First row is a11 minus x, a12, a13 plus up to a1n. Second row is a21, a22 minus x, a23 plus up to a2n plus dash dash dash. Last row is an1, an2, an3 plus dash dash dash. Last element is ann minus x. This is A minus xi. Clearly, the elements of A minus xi are at most of the first degree in x. Hence, the elements of adjoint of A minus xi are the ordinary polynomials in x of degree n minus 1 or less. Therefore, adjoint of A minus xi can be written as a metric polynomial in x which is given by adjoint of A minus xi equal to b0 plus b1x plus b2x square plus up to bn minus 1 x raised to n minus 1, where b0, b1, b2 up to bn minus 1 are square matrices of order n. Now, you know that the property A into adjoint of A equal to determinant of A into I. We use this property, hence we have A minus xi into adjoint of A minus xi equal to determinant of A minus xi into I. Denote this equation as equation 1. We observe that determinant of A minus xi is a polynomial in x of degree n, as determinant of A minus xi equal to a0 plus a1x plus a2x square plus up to an x raised to n. Hence, RHS of equation 1 equal to, RHS of equation 1 is determinant of a minus xi into I, which is equal to, in bracket, a naught plus a1x plus a2x square plus last term is an x raised to n bracket complete into I. I means identity matrix of order n. Hence, RHS of equation 1 equal to a naught I plus a1 into ix plus a2 into ix square plus last term is an I x raised to n. Denote this RHS of equation 1 as equation 2. Again consider the LHS of equation 1. From the previous term, you know that LHS of equation 1 is a minus xi into adjoint of a minus xi, which is equal to a minus xi. Adjoint of a minus xi is in bracket b naught plus b1x plus b2x square plus up to last term bn minus 1 x raised to n minus 1 bracket complete. That means adjoint of a minus xi is taken from the previous equation. After simplifying these two brackets, we get LHS of equation 1 equal to ab naught plus in bracket ab1 minus b naught bracket complete into x plus ab2 minus b1 in bracket into x square plus last term is minus bn minus 1 x raised to n minus 1. Denote this equation as equation 3. By using equations 2 and 3 in equation 1 is a minus xi into adjoint of a minus xi equal to determinant of a minus xi into I. Using these equations 2 and 3 in equation 1, we get ab naught plus in bracket ab1 minus b naught bracket complete into x plus in bracket ab2 minus b1 bracket complete into x square plus last term minus bn minus 1 x raised to n minus 1 equal to a naught into I plus a1 ix plus a2 ix square plus up to last term is plus an I x raised to n. Now comparing the coefficients. Comparing the coefficient means here we have to comparing first the constants on the both sides. Then comparing like powers of x, that is comparing powers of x raised to 1 on both sides, and then compare powers of x raised to 2 on both the side, and so on. So comparing the coefficients, we get equations as ab naught equal to a naught into I. This term comes from comparing constants from the both sides of above equation. The second equation is ab1 minus b naught into equal to a1 into I. Second equation is ab2 minus b1 equal to a2 into I, and so on. And the last term is minus bn minus 1 equal to an into I. Now multiplying the above equations by I, a square up to a raised to n respectively, and adding we get, that means ab naught multiply ab naught equal to a naught I by I, then multiply ab1 minus b naught equal to a1 into I, this equation by capital A, multiply the equation ab2 minus b1 equal to a2I by a square, and the last equation minus bn minus 1 equal to ani by a raised to n, and after adding we get 0 in the LHS side, 0 equal to a naught I plus a1a plus a2a square plus up to last term is an a raised to n. Thus we get a naught I plus a1a plus a2a square plus up to an a raised to n equal to 0. That means every square matrix satisfies its characteristic equation. You know that characteristic equation is a naught I plus a1x plus a2x square plus anx raised to n equal to 0. Every square matrix satisfies this equation means replacing x by capital A. This equation is satisfied. Hence, from this equation a naught I plus a1a plus a2a square plus up to an a raised to n equal to 0, we get that every square matrix satisfies its characteristic equation. Thus, the theorem is proved, which is known as CAYLEY-Hamilton theorem. Now, we consider one example. Apply CAYLEY-Hamilton theorem to matrix A equal to square matrix of order 2 by 2. First row is 1, 2. Second row is 2 minus 1. And deduce that means prove that a raised to 8 equal to 625 into I. Here consider in the solution, first write given matrix A equal to 1 to 2 minus 1. Every square matrix satisfies its characteristic equation, means determinant of A minus lambda I equal to 0. Hence, consider the characteristic equation determinant of A minus lambda I, that means subtract lambda from the diagonal elements. Hence, we get determinant 1 minus lambda 2. Second row is 2 minus 1 minus lambda equal to 0. Solve this determinant so that we get the equation as 1 minus lambda square plus 4 equal to 0, that is lambda square equal to 5 is the characteristic equation of given matrix A. CAYLEY-Hamilton theorem says that every square matrix satisfies this characteristic equation. That means after replacing lambda by capital A, we get A square equal to 5. That is A square equal to 5 into I. That is I is identity matrix. A square equal to 5I. That means every square matrix satisfies its characteristic equation. Hence, squaring both sides we get A raised to 4 equal to 25 into I. Since I into I is I square, it is also equal to I. And also taking next power, we get A raised to 8 equal to 625 into I. Thus, we have proved the required result. Thank you.